Good morning, lovely 12ers. Right, buddies. I hope you enjoyed the last lesson on proof by induction. It is really cool. I know there's a lot to get your head around and stuff with it, but I hope that you enjoyed it. And today, what we're going to do is we're going to talk about other types of proofs. Well, not other types of proofs, but other types of examples of proof by induction that you can do. I know all the ones that you did last time were linked to series. That was a whole bunch of numbers added together following a pattern, following a rule. That's what a series is, as you guys know. And we've only done proof by induction with series. Well, to be honest, you can use proof by induction in a whole bunch of different circumstances, okay? Proof by induction is good for whenever there's kind of an infinite number of cases of something, okay? So things like sequences as well, so we don't have to restrict ourselves only to series. Sequences work as well, like the sequence in question 1 here. And there's also things like raising stuff to a power. There's proofs that you can, I'm trying to remember what it is. There's a proof you can do with Fibonacci numbers that uses proof by induction as well, and it's just really cool. Essentially, whenever you get a variable in, which is defined to be a natural number, so whenever you get a counting variable in, oftentimes in those cases, proof by induction is the way forward. So, before we start this question, let's just see if you can remember. There were 6 steps. Do you remember what they are to proving something by induction? Well, if you said step 1 was establish a base case, so you show that you can take a step onto the ladder. Step 2, it reveals everything when I do that. Step 2, presume it works for all values of k. Then, of course, you get your target expression. Following that, what do you do, my buddies? Well, you actually start proving it. You start from the left and you try to prove to the right, okay? So you work with your left-hand side and you prove that you can actually get your target expression before you can make your statement. So you've got to state why proof by induction works. It's not quite enough to just say it's proof by induction. You got to say why it works every single time, and then make your conclusion just by restating what you already had. So, boom, you remember proof by induction. Cool beans. So here we go. First ever non-series proof by induction. So here we go. Let's read it. It says, a sequence is defined by this. Okay, so it is, does anyone remember what that's called? Anyone want a brownie point with me? When it's got, when you've got, it's a sequence, but it's like the next term, because it's n plus 1, is equal to 4 lots of the current term take away 3. Anybody remember what that's called? That's right, it's a recursive sequence, isn't it? It's defined by previous terms. That makes it recursive. And it also tells you, my lovelies, that the first term is equal to 2. Okie dokie. And that's that. Now, what we're asked to prove is the nth term, which is that. So we're trying to show that the nth term is equal to that. My highlighter brush is too thin today. It's too much coloring to color this in. Okay, so there you go. Let's see if we can do it. Well, whoops. What's step 1 again, buddies? Who remembers step 1? That's right, base case. So here we go. Let's do this thing. Let's go in blue. Let's live dangerously and use blue. Okay, so, and again, you don't have to put the numbers down. Shall I bin off the numbers this time? I'll bin them off next time. I'll show them this time. Okay, base case. Okay, we need to show that this works for at least one number to start with, because remember, that's what we're doing. We're establishing it works for at least something. So here we go. The base case is usually easiest to have n equals 1, okay? So here's what you're going to get. On the left-hand side then, so on the left-hand side, LHS, we're just going to get then, because this is the thing we're trying to prove, in green I mean, the left-hand side is just going to equal U1. Okay, that's all it says. We're not using the right, just the left. The left-hand side equals U1. But U1 was defined up here in blue, so it's 2. See what I mean? It's just defined in blue. Cool. Well, what does the right-hand side give of the green? Well, the right-hand side of the green was 4 to the power of n take 1 plus 1, but n is 1. 1 take 1 plus 1, which means it's going to be 4 to the power of 0 plus 1, which means it's 1 plus 1, which means it's 2 as well. Confirmed. We have a base case done. What's the next step, buddies? The most important step of all. That's right, you assume that it's true. For n equals k. Okay? Presume that it's true for n equals k. Because if that were the case, it would mean that u to the k is equal to 4 to the k minus 1 plus 1. So if that's true, then that's the case. Cool beans, buddies? And here we go. Now, if that's true, remember how induction works, the next step is to show that it works for the next one up. So this is a general step on the ladder. So if it works for the general step on the ladder, we need to get what the next step is. So if it works for this rung, you've got to show it works for that rung above it as well. Hooray, I knew Scruffy would come in handy from Futurama. So there we go. So let's do it. So we are going to 3. That's what we're going to do. So here we go. What do we do first? Well, we're going to get a target expression. Okay, expression. Now, the target expression is what we're going to actually try to get to, and it's going to be for n equals k plus 1. Okie doke. Now, if that's true, then here's what we got, my buddies. We are going to get, what are we doing? We are going to get, oh, my brain is just frozen for a moment. Oh yeah, well here's what we're going to get. We're going to put k plus 1 in. That's k plus 1 in. That's what we're going to do. Well, here's the deal then. U to the k plus 1 then, my buddies, I'm going to switch back to blue. U to the k plus 1 is going to be this. U to the k plus 1, so just putting k plus 1 into the original up here, is going to equal 4 to the power of k plus 1, take 1, plus 1. Cool? Which means on the right-hand side, we're gonna end up with, I'm going to squeeze it in, u to the k plus 1 equals, and it's going to be 4 to the regular k, but not with the plus 1, plus 1. Cool? That majestic thing there, my buddies, is your target expression. So if we can get the left-hand side to equal this, then we've done it, okay? So the left-hand side, if this conjecture is true, then the answer should be 4 to the power of k plus 1. Cool! So now we're on step 4, buddies, proving it. Prove from, I usually put left-hand side for the series ones, but we're kind of proving it from the original thing. Prove from, I'm going to write original this time. Okay, so in other words, I'm not going to, instead of writing from the left-hand side, on this one, what I'm going to do is, we know for sure this is a fact, what's in the yellow, right? That's defining our sequence that we're dealing with. It's u to the n plus 1 equals that. If we can prove from this, from the yellow, and show that we get the target expression from the green, then that's how we're going to prove it, okay? So we're going to prove from the original. So here we go. From the original then, here's what you've got. The original was u to the n plus 1, but we're going to be using k plus 1. So here we go. It's going to be u to the k plus 1, and on this side, it's going to be 4 lots of u to the k minus 3. So that's from the yellow, okay? Can you see that? That we're working from the yellow. Now, my goal is that it will equal up with the target expression when I'm done. So we're going to make the yellow one equal up with the target expression. So let's do it, buddies. So if that's the case then, my buddies, here's what we got. That means that u to the k plus 1 is going to equal, and it's going to be 4u to the k minus 3. But we assumed something, didn't we, my lovelies? What's u to the k equal to? That's right, it's the target expression, isn't it, my buddies? So it's going to be 4 lots of 4 to the k minus 1 plus 1, that's it, minus 3. Now, really importantly, we don't know that this assumption is true, do we? We've not proved that yet. So what we're going to put down is from assumption to really define that. From assumption. Okay, so we don't know that that's necessarily true, but we're carrying on. If it equals that, then it was true, but we don't know that yet. So here we go. That means u to the k plus 1 then is going to be equal to this. This is going to be 4 times 4 to the k plus 1. Well, I'm going to show that as an extra step to make sure you guys get it. Well, it's just going to be this. It's going to be 4 times 4 to the k minus 1. And it's going to be plus 4 when you times it onto the 1, minus 3. Okay. My buddies, what can you do with these things here? What is this 4 to the power of? That's right, 1! And because they've got the same base, you can add them together. So it's 1 plus, so it's going to be 1 plus k minus 1, which means it's just 4 to the k. Oh my gosh. Which then you've got plus 4 and minus 3, which equals plus 1. Well, oh my gosh, buddies. Does that look familiar? Yes, it does. It's the target expression. Oh my gosh, we've just proved it. So let's do our statement. Okay, here's our statement. And here's the statement. If the result is always the same, is true. True for n equals k. For n equals k, in other words, if our assumption is true, then it's also true for n equals k plus 1. Okay, and that's what you just proved. So just to really make sure you got your head around it, if this is true, then this is true as well. If the assumption is true, then the next one is true above it. Then the next one above it as well is also true. So if it's true for that, it's also true for that. Now here's the big killer. Since it's true for n equals 1, then that means by necessity it's true for n equals 2, because if it's true for one thing, it's true for the next thing. You've already proved that for n equals 2. And continue the logic on. And if it's true for 2, it's true for 3, 4, 5, 6, 7, 8, 9, a million and 1. It's true for all of those. It's true if it was, and I've got muddled when I was saying, since it's true for when n equals 1, it's true for n equals 2 and all positive integers. Positive integers. Okay, and that's almost there now. That's the last of the real stuff. And then 6. Then you just got to restate it. Thus, and here we go, u to the n is equal to 4 to the n take 1 plus 1 by mathematical induction. By mathematical induction. And I know it's a faff, but it's a proof, so it has to be thorough. And that's exactly what this is thorough. So really good work if you got that. I hope you got your head around it. This is interesting, I think. Maybe you'll find it interesting. I hope you do. You're further maths kids. You might find it interesting. That's quite good, though. That's a really important result that you proved, because this formula in yellow is a palaver. Who wants that? That's rubbish. You can't actually figure out what the nth term is unless you know what the term before the nth term was. This yellow formula is absolute rubbish. Whereas this one here, if I wanted the 1000th term, I could just pop 1000 in. If I want the 6th term, I could pop 6 in. The green expression is way more powerful than the yellow one, and so we used maths, we used proof by induction to turn a rubbish recursive formula into a beautiful kind of explicit formula, which is cool. Hooray! And look, we didn't even need the bonus page that I was going to fill in extra steps on. Woohoo! Okay, here we go. Harder still, my buddies. Check it out, matrix question. Now, you have learned matrices, so I looked this up on the scheme of work. I'm going to teach you some more bits and bobs with matrices after this unit, but at the moment, you do know how matrices work in terms of adding them, when you add each component together, multiplying them, where you do that weird thing where it's like columns by rows, and so on and so on. So you should be able to do this. We will be able to do this, and here we go. It says, given that A is equal to this, prove by induction that that's equal to that. Now, this is only going to be true if this is going to be true for n being a natural number, okay? A counting number. So I think they're wanting you to raise it to whole powers. That's what they want. It needs to be that in order for the multiplication that we're going to do. So they didn't state that, which they almost, I suppose, could have. No, I don't know if they needed to state that or not. But anyway, where n is a whole number, okay? So we're counting on irregular whole numbers. But here's what I want you to do. If you're feeling brave and you're feeling like you do remember how to do matrices, go ahead, pause, get ahead of me and see if you can do it. Go. And if you're not, let's do it together. So here we go. Let's do it. It's mathematical induction. Let's crush it out. Let's try. So first step, my buddies, and I'm not going to use the numbers this time, base case. Now, if you're going to do a base case, that's when n equals 1. So here we go. Well, our thing that we're trying to prove is this bottom palaver here. It's this whole majestic bad boy here. That's what we're trying to prove. And so here we go. Let's do it. From the left-hand side, if we put in 1, the left-hand side of the what's in yellow is a to the power of 1, which is just a. And a was equal to, from the top part, 4, 1, 3, 2. 4, 1, 3, 2 as a matrix. Cool. Now, does that match up? Does it match up with the right-hand side? Well, let's see. Let's go right-hand side. Well, on the right-hand side, here's what we've got for n equals 1. Well, there's a quarter touching the matrix. In the matrix, we'll have 3 times 5 to the power of 1 plus 1. 3 times 5 to the power of 1, take 3. Oh, yeah, sorry, 5 to the 1, take 1, and then 5 to the 1 plus 3. So let's see what that equals. It's going to be a quarter of, and here we go. 3 times 5 is 15, 16 it's going to be. 3 times 5 is 15, 14, 13, 12. Here we've got 5 take 1 is 4, and here we've got 5 plus 3, which is 8. And the quarter out front, you guys remember, multiplication by a scalar, by just a standard old number, not a matrix. You just divide each one by 4. You could times each one by a quarter. That's how it works. So it's 4, 1, 3, and 2, which does confirm, doesn't it? So it matches. Base case established. It does work on both sides. Cool. Next up, what is it, my buddies? That's right. You assume that it works for n equals k. Cool. Because if you assume it works for n equals k, here's what you're going to find. You're going to find then that a to the k, lots of writing. This is going to be a page's worth of one. I can feel it. A to the k equals quarter, and it's going to be 3 times 5 to the k. It is necessary to do this, unfortunately, plus 1. 3 times 5 to the k. Take 3. 5 to the k minus 1, and 5 to the k plus 3. So there is our assumption, okay? Now, oops, now this we will definitely have to use because that's the crux of the entire thing. So I'm going to put an asterisk next to it now just so we can remember it. Okay, in case we need to in case we get lost later on. Oh my gosh, I'm having trouble spitting it out here today. Ooh. Okay, next step, what is it? That's it, target expression. Cool. Now, that's basically saying if you did raise it to the k plus 1, what would the answer supposed to be if the assumption's right? Okay, so if the assumption were right, what would we end up with? Well, a to the k plus 1 then would be, and we're going to actually use the assumption, or use what's up there in yellow, both are cool. It's a quarter, and it's going to be open brackets. It would be 3 times 5 to the k plus 1 over 3 times 5 to the k minus 3. Then we're going to get 5 to the k plus 1, take 1, and 5 to the k plus 1 plus 3. Okay, and that's brilliant. That's going to be our target expression. Now, to be honest, my brain is reeling right now at the moment because I'm trying to think, do I actually want to split this up and get it in terms of k? I might do, I don't know yet. So I'm going to go with, so essentially, should I rewrite this as 3 times 5 to the 1 times 5 to the k? Would I like to do that? I don't know. It would be better, to be honest. I think that might be simpler. I'm going to. I wasn't going to, but now I'm going to. So I am. Okay, here we go. Target expression. Quarter. So this could be good as a final target expression, but I'm trying to imagine what I'm going to do ahead of time, and I think having the k plus 1 is going to be harder to show than just having the k, so I'm going to get rid of the k plus 1s, my buddies. Oops, and I forgot a plus 1 there. So here we go. I'm going to tidy it. I'm going to rewrite this as 3 times 5 to the k times by 5 to the 1, okay? Plus 1. Then we're going to get 3 times 5 to the k times 5 to the 1 minus 3. Then we're going to get 5. I think I'm making the right choice here, just for the record. I should have read the answer to the proof before I started. But this is good. Okay, and then this one here is going to be 5 to the k times 5 to the 1 plus 3, which means that we're going to get a quarter. And we're going to get here 3 times 5 is going to be 15 times 5 to the k plus 1. Here we're going to get 3 times 5 is 15 times 5 to the k, take 3. This one here we're going to get 5 times 5 to the k minus 1, and here we're going to get 5 times 5 to the k plus 3. Now, I'm hoping, I'm fingers crossedly, I'm hoping that this is a better form to have it in than 2 lines above, but we'll have to see, I guess. Okay, so now what we're ready to do is we're ready to actually prove, okay, my buddies? So here comes the flicking between slides. We're going to prove, okay, from the left-hand side. So we have to prove it. So prove, okay, from left-hand side. Left-hand side, okay? So it is going to be the left-hand side this time. So looking at the thing that we're trying to get, let's go to the left-hand side. It's just going to be a to the power of n, so we're going to prove it with the k plus 1, okay? So it used to be a to the n, now it's going to be a to the k plus 1. Okie dokie, my buddies. So what I'm going to say then, my buddies, is this. We could rewrite this then, because it's just powers, okay? Now the order does matter with matrices, but they're square matrices in this case, so it's actually okay. So here we go. That's going to be the same on the left-hand side as a to the k times by a to the 1. Do you guys agree? Cool. But we know for sure what a to the 1 is. It's this, right? That's just a. And actually, from our assumption, we know what a to the k is. A to the k is this. Okay? So, here we go. This is going to be lots of flicking back and forth. What was it? What on earth was it? It was a quarter, and then it was matrix of 3 to the k, or how can I make this bigger so I can see both at once? Oh, look at me cheating. I like that. So it's a quarter. I can see it on this slide now. Okay. 3 times 5 to the k plus 1. 3 times 5 to the k minus 3. 5 to the k minus 1, and 5 to the k plus 3. So that is from the assumption. We also knew that a itself, buddies, was 4132. 4132. 4132. Okay, and you do have to say in this case from assumption, because we did use the red, didn't we? Right, now we've got to go algebra mad, my buddies, to try to get the target expression. So let's do it. First things first is I'm absolutely chilling the quarter, because I cannot be fussed with that at the moment, I'm not going to lie. So let's leave the quarter, I don't like that at all. And here we go, it's time for some horribleness of matrices. I'm going to write it enormous, and I'm going to take up this whole page. Okay, remember how matrices work? So it's going to be this times this plus this times that. Remember all this rubbish? So it's like this times this, and then it's going to be this one times that one. Remember how that goes? So here we go. Let's do it. So here we go. It's going to be 3 times 4 to make 12 times 5 to the k plus 4 is what we're going to get there. And then this one here is going to then be plus, and it's going to be 3 times 5 to the k minus 3. So that's our first one. Whew, already hard work. Okay, I'm going to get rid of the colors here because I think they're going to distract me if I keep using them. So here we go. To get the second one, we are going to go with the 1 and the 2 rather than the 4 and the 3. So let's do it, buddies. So 3 times 1 is just going to be 3 times 5 to the k plus 1. It's just going to stay the same. So that's that with that. Now we're going to go plus, and it's going to be 2 times 5 to the k. Minus 2. That's that one. Next one. 3 times 4 is 12 times 5 to the k minus 12. This by that. Okay, plus, and here we go, 3 times 5 to the, oh yeah, is this one by that one? Yes, that's right. 3 times 5 to the k plus 9. So there's what we got there. And finally, the last columns, we're going to go, the last column that we're going to do is the one with the 2 column, isn't it? Yeah, so we're going to go this by them too. So it's going to be 3 times 5 to the k, take 3 because it was just times by 1, and then the second one it's going to be plus, and we've got 5 times 2, so 2 times 5 to the k 2 times 5 to the k plus 6. Oh, I so hope that that's right, because it is a palaver. Okay, I'm going to keep the quarter chilling. Oh my gosh, it reminds me of the simplex rubbish. Does it remind you too? Okay, so let's do it. Here we go. First things first is we've got a 12 and a 3 to make a 15 here, okay? So there's 12 of the 5 to the k's plus 3 more of the 5 to the k's. So there's 15 of the 5 to the k's. Plus 4 minus 3 is plus 1. Okay. Next bit, what we're going to get here is we have 12 of the 5 to the k's plus 3 to the 5 to the k's is 15 of the 5 to the k's, and then we have minus 12 plus 9, which makes minus 3. Okay, next one, we have 3 of the 5 to the k's plus 2 of the 5 to the k's are 5 of the 5 to the k's. I'm so pleased that I switched my target expression over. 5 of the 5 to the k's, and this is minus 1. And we have 3 of 5 to the k's and 2 of 5 to the k's, which makes 5 of 5 to the k's. And then we've got minus 3 plus 6, which is plus 3. Which, oh my god, my lovelies, isn't it? How exciting! It's 15 times 5 to the k plus 1, 15 times 5 to the k plus 1. Oh, actually, you can see them both on the screen at the same time. That's right. That one's right. That one's right. That one's right. Oh my gosh, we've done it. We've hit the target expression. We've got the target expression. So, in other words, if the assumption was right, the next step after the assumption's already right, which means we're ready for our last step, our second to last step, the statement, which is this. It's always the same. So, if result is true for n equals k, then it's true, for n equals k plus 1. You get that we just proved that, right? So if the assumption we assumed was true, and if the assumption was true, the next step is also true. But that means since n equals 1 is true, since it's true for n equals 1, then that means, because the next step is true, it's true for n equals 2, and 3, and 4, and 5, and 6, and all positive integers. Alrighty. Whew. And here we go. And the final mark is this. Thus. Oh, a to the power of n. There's one more kick in the teeth, this one, my lovelies. One more horrible time writing it. Thus, a to the n is equal to, and I can see it from the slide before, from the big thing on the left here. That's why I'm doing this. A to the n is equal to, I'm just copying it from the question, a quarter. 3 times 5 to the n plus 1, 3 times 5 to the n plus 1, 3 times 5 to the n take 3, 3 times 5 to the n take 3, 5 to the n take 1, 5 to the n take 1, and not the take 1 is not in the power, 5 to the n take 1, and 5 to the n plus 3. Boom. And why? By mathematical induction. Whew! Amazing! They're fun, aren't they, though? They are fun. You gotta use your brain. It's a lot of writing, but you gotta really use your brain. And I just really enjoy the logic in them, to be honest. I like the statement. That's my favorite part. I like getting the target expression. I like the statement. They're both good. It shows that you're pro at logic. So, for the rest of the lesson, page 92, question 1 to 9, do a mix. This does finish the induction unit, but next lesson I'm going to give you a whole practice lesson to practice, okay? So I'll go inside, see if I can find you some different unique work, and then you can just practice proof by induction, because, I don't know, it's a really good skill and it's fun to do, so happy days. So that's it, my buddies. That's it from me. Take a photo when you're all done your work, and that's it from me. See you later. Bye, buddies!